Hello everyone. In this video we're just going to be working through some problems of Unit 1 of AICE Physics. So these are just past paper problems. So without further ado, let's go ahead and do this problem. So when a constant braking force is applied to a vehicle moving at speed v, the distance d moved by the vehicle and coming to rest is given by the expression d equals kv squared, where k is a constant. When d is measured in meters and v is measured in meters per second, the constant has a value of k1. What is the value of the constant when the distance is measured in meters and the speed is measured in kilometers? Okay. So this is our initial condition kind of thing. So initially we have d is measured in meters and then v is measured in meters per second. Then k1 is the constant. So then they're asking the value of the constant when the distance is measured in meters and the distance is measured in kilometers per hour. So let's say this new k is k2 is equal to meters and then kilometers per hour squared. So we need to convert it so that this is in meters per second and this is in meters. Well, this one is already in meters, so we don't have to do anything, but we have to convert these ones. So then we have this equation. Let's actually distribute it out, so I don't write the same thing twice. And then we need to simply convert these. Since I'm not really used to notation, I would just use fractions to just further exemplify the point. So hours squared, and then we can do with simple dimensional analysis. So we can just say like these are 1, and then this is 1 kilometer squared is equal to 1,000 meters squared times 1 hour squared over 360 squared of seconds. So just to reiterate, so since these units are squared, these conversions are also squared. So then we can simply just plug into our calculator. 1,000 squared divided by 3,000 squared, because everything is essentially 1. So then we get m equals k2 times 0.077 to sig figs ish, and the problem is 3, so we can just do 3. So then we know that the unit in the back here is just meters squared per second squared. So then we have this equation right here, and then we also have our initial equation. I didn't write it down, but it's simply meters is equal to k1 times meters per second squared. So then we can just simply compare the k values right here and right here. And then we can just say it's that. Let's see if it's right. So yeah, the answer to this question is A. Just make sure it's the right one, and pretty much it is. Yes. Next question. The arrow represents vector R. which diagram does not represent R as two perpendicular vectors. So in general, when we're adding vectors to perpendicular components, there's usually a resultant vector where you take this vector and put it at the end of the others. So you take the tail of one vector and then you move it to the head of the other, and then you get a new resultant vector. So they're just saying which diagram does not represent R as two perpendicular components, which is simply just saying which two vectors, when added to each other, is not R. So for example, like I did this. So we can take this vector here. Ooh, that's not a straight line. And then we can move it over here. So then we get the same height. And then our resultant vector is like that, which is similar to R. So we can just like take it for granted and say it's close enough. And then our next one, here B, we can do the same thing. Just make sure it's parallel. So we take the tail, we take this vector, and then we just move it to the head of the other vector, like that. And then our thing is pretty similar to the initial two vectors, so it's just like that, and it's kind of like R. It's going the same direction, and it's like kind of in the same way. So then let's go to C. So we have this long vector going down, but we can just move it up here like that. It's not necessarily parallel, is good enough. And then we can say that this is our new vector, and obviously it's actually going down instead of going up. So we can just technically stop here and then say that it's C. But I will just demonstrate the second one just to make sure, because in terms of AICE questions, they are somewhat tricky, and it's like important to check your answer. So this is D. This would be the vector. And then R. And then you can see that it is also still in the general direction with a similar amount of length. Oops. Huh. It is C. The arrow represents vector R. Okay, next question. The speed of the aeroplane in still air is 200 kilometers per hour. The wind blows from the west at a speed of 85 kilometers per hour. In which direction must the pilot steer the aeroplane in order to fly due north? Okay. So, basically, if we can see the question says that we want the aeroplane to fly due north. So that means that our resultant vector has to be due north. But we just don't know like exactly what the angle is. So let's say this is the airplane. This is flying at a certain direction. And then we just need to find this angle. Oh, I did not mean to draw a heart. Okay. But this is like in general what this problem is talking about. So now we just need to like take the information they actually give us and then apply it. So the speed of the airplane in still air is 200 kilometers per hour. So we know that the magnitude is 200. And the wind blows from the west at a speed of 85. So blows from the west. So that means it starts from the west and goes east. And this is 85 kilometers per hour. And then we want to make sure that this 85 kilometers per hour plus our 200 vector in some direction is equal to due north, just due north. It doesn't matter the magnitude, but we just want it to due north. So if we draw this diagram, we can just say that our thing here is 85, and then our airplane is actually moving this way, so that it neglects the western change. And then this is the diagram that we should draw, basically. And then now we need to calculate the direction. So simply just glancing at the answer choices, it says of north, of north, of north, of north. So that we should just calculate based on the north. We can simply redraw this as this. And then this is our angle. So then we can say that tan inverse of 85, actually this is not tan, this is sine. Remember your SOHCAHTOA, guys. Sine inverse of 85 over 20, 200. Make sure your answer is in degrees too. I believe AICE wants degrees always on your calculator. So this is about 25.2 degrees. And then you want to start on which side. So let's say that we're going off the north, right? So our second number is going to be north, and then we want to say left or right, or west or east in this case. So since we're going west, it's going to be west of north, which is D. Okay, an FRQ problem. A boat travels across a river in which the water is moving at a speed of 1.8 meters per second. The velocity vectors of the boat and the water are shown in scale. Draw a vector diagram. So to get the resultant vector of the boat, we simply just need to add the two vectors that they give us, which is this boat velocity and then this water velocity thingamajiggy. So we can go ahead and do that. Please be straight. Okay, there we go. So this is our water velocity. We take the tail of the velocity and then put it at the head of the other vector. And then we can say that, yeah. Be there. Yep, okay. And then this is the resultant vector. Determine the magnitude of the resultant velocity of the boat. So since this is a two-dimensional diagram, we're gonna have to break it up into X and Y components. So my notation is kind of weird, but it's generally the same thing. So I write it in these order pairs where this is the v of x and this is the v of y. It's like an ordered pair. So our water velocity, it only goes west. So we can say that our y vector is nothing. because it doesn't go up or down, it only goes left to right, but it only goes left at 1.8 meters. So this is our water vector. And then now we have our boat vector. They actually give us an angle of which our boat is traveling. So v of x is equal to 3.0 meters per second times cosine, because this is the x direction. Since it's x, we use cosine of 60, which is 1/2, I think. So it's 1.5 meters per second. And similarly, we have our 3.0 meters per second times sine of 60. And this one I can't do in my head, unfortunately. And then we have 2.598, and we're gonna round to 2 sig figs because that's what Cambridge wants. So then our resultant vector is just simply 1.5, 2.6. And after that, we need to add the water in the boat. So the water plus boat, how do I spell boat, is equal to negative 1.8 from the water plus 1.5, 2.6. So these are just our x and y components, and we just add the x components together because those are like the way it works, yeah. And if we add it, and then they want the magnitude of the resultant vector. So we have our x and y components, and we can just simply do Pythagorean theorem because these two are perpendicular to each other. So then we just calculate this. And then we get about 2.6. Technically 2.62, but it's good enough. So this is our answer. Okay, a boat is traveling in a flowing river. Shows a fig 1.1 shows the velocity vectors for the boat in the river water. The velocity of the boat in still water is 14 meters per second to the east, and the velocity of the water is 8 meters per second from this. So these are just our two things. On fig 1.1, draw an arrow to show the direction of the resultant vector velocity of the boat. So basically we do the same thing. Instead, in this case, I'm actually gonna draw the boat velocity on this side. So we have this long thing. Let me just say up here, about. Sure, around here. So this is our boat velocity. And then thus our resultant vector, hello. So this is our resultant vector. Don't forget your arrow to show where it's going. Determine the magnitude of the resultant velocity of the boat. Okay, so this problem is actually really similar to the problem that we just did. We need to break it up into our x and y components. And then after that, we need to find the x and y components of the resultant vector, and then calculate the Pythagorean theorem. Okay, so let's calculate each one individually. So the water is actually going down 60, and at a 60-degree angle here. So we can translate this as in this vector here and this vector here. So it's actually going left and it's going down, so that means both of them are actually negative. I should reiterate that the water magnitude is 8 meters. So the v of x of this is 8.1 meters times cosine is 60. In reality, it should be, I believe it should be 240, because if this is our xy plane, the angle is actually this. And this just means that our component is equal to negative 4 meters per second. And then Vy is equal to 8 point this times sine of 240 is equal to negative 6.9. And then we can calculate our boat velocity. And we know that boat is going right, so we can just say it's just 14 meters per second. And there is no y component. So then we have our x components and our y components, and we just add up our x and y. So our v x, I guess like final, I don't really know how to notate it, but it should be negative 4 plus 14 is equal to 10, and then vyf is equal to negative 6.9. And then after that, we do a Pythagorean theorem to get the magnitude is 6.9 squared. That's calculator. No. Which is about 12.1 meters per second. Technically it should be 12 because you always round to 2 sig figs. So yeah. So basically what we did is that we added our two vectors to get this resultant vector. And to get the resultant vector, we have to add up the individual x and y components of each vector. So we calculated that. And then we added the x and y components of each vector. So we get our resultant vector. And then we calculate the magnitude by taking the square of each component and then square rooting the final sum. Okay. So now 3 wires exert a horizontal force on a vertical pole as shown. I'm good at poles. Which vector diagram shows the resultant force R acting on the pole? So when you're calculating the resultant force, we have to add up the vectors. In this case, it's a little bit hectic since we have 3 vectors instead of 2. But not to worry. Let's take each vector at one at a time. So let's take this vector first, for example, and then we're going to move it its tail to the head of the one that we want. So then this is done. Okay, and then we'll take this new vector, cross it out, and then add somewhere around this. So then our resultant vector is here. And then we'll look at the answer choices to see, oh, this one actually looks exactly like the one we just drew. So the B is the answer. And then we'll just check the others just to make sure we're not crazy. So a simple sanity check is that these two vectors on the side I should like point it out. So these two vectors are much greater than this vector. So then we can say, like, since these vectors are so strong compared to this small vector, we can tell it's generally going down southeast. And then the only one that actually matches is this one, but you can see like this force is too massive. This one is our correct answer. This is going the wrong direction. This is also going the wrong direction. So we can say our B is our final answer, and we're pretty confident in that. Number 7, the diagram shows two vectors, x and y, drawn to scale. If x equals y minus z, which diagram best represents the vector z? Okay, so even though it doesn't seem too intuitive, these things, you can actually rearrange this equation just like an algebra equation. So we have x equals y minus z, but we want z. So we can just isolate z by adding z to both sides and then subtracting x. So z is equal to y minus x. So then we have x and y, and then all we need to simply do is just add these two vectors. If you're confused about how to subtract a vector, the negative is simply the same thing as this. So we're just adding the negative vector of x. So let's say we have a vector v. Negative v is just going in the opposite direction. And this is the idea that this question is trying to test. So we know our x is going this way, but now we want our x to go this way. So that after that, we have this x, negative x, and then we can draw our resultant vector here, which is just going to be z. And then we can see that the only one that actually satisfies this is A. A girl runs 120 meters due north in 15 seconds. She then runs 60 meters due east in 12 seconds. Sketch a vector diagram to show the path taken by the girl. Draw and label her resultant displacement. So I'm actually not going to use their diagram because it's too small. So we have, okay, I should do this in a different color. So we have our 120 meters here in 15 seconds. So this is the magnitude, and then we have due east, right? Yep. So this is our diagram, basically. In the XY plane, of course. And generally, if you don't want it like drawn in an XY plane, we can just simply say like this is our north vector. In terms of displacement, and then this is our eastern vector. And this is our resultant vector. This is 120 meters, 80 meters. I may have said velocity, but in this case, this is displacement, so we don't actually need time. Just ignore this. Sorry. So calculate for the girl the average speed. So average speed is distance over, actually total distance over total time. They actually gave us both of these information. So we can say the first part, she she ran for 120 meters plus 80 meters, and then we can say 15 seconds plus 12 seconds. This is 200 meters over 27 seconds. And you can just quickly plug that in, which is around 7.4 meters per second. So and now they want the magnitude of the average velocity and its angle with respect to the direction of the initial path. Okay, so they're actually asking for two things here. So they want the magnitude and they also want the angle. So we actually have our resultant vector, and now we just need to actually calculate the velocity. So since our initial diagram talks about displacement, we just need to divide it by our time to get our velocity. So let's redraw this diagram. So then we know that the magnitude, oh wait, I think I should like clear this up, but this is displacement. It's easy to get confused, so you have to remember what you're talking about most of the time. So we're going to calculate displacement. Which is around 144 meters. And then since velocity is displacement over time, we can simply just divide it by our time, which was calculated up here. 27 seconds, which is around 5.3 meters per second. And then now they want the angle in respect to the direction of the initial path. So then we just want the angle, remember it's an initial path, so we have to go off this north. So we're in fact calculating this angle right here. And this angle is equal to the tan inverse of 80 over 120. Which is about 34 degrees. Yep. So just remember that displacement over time is equal to velocity. So we took our displacement, total displacement here. This is our displacement, and then so we took our displacement over time, and then we got our average velocity. So the diagram shows two x and y vectors. The vectors are perpendicular to one another. What is the magnitude of the direction and direction of x minus y? So we did kind of go over this in a previous problem, but this is simply x plus minus y. So we have x minus y, so all we need to do is take this arrow and then put it on this side, and then it drew a little heart. Nice. And this is our y, 6.0, and this is our resultant vector, and they want the magnitude and direction. So our magnitude is equal to the square root of 6.0 squared plus 8.0 squared, which is around 10. You can check the calculation. And then the angle, let's look at this first. So we see that 37 downwards from the direction of x, so basically east, so up, down. So it's obviously going to go upwards because this direction is going up, so we can eliminate these two answers because we know for sure they're not it. And then we can just do a rough calculation. So our angle is equal to 6.0 divided by 8.0, which should be 37 degrees, which is B. If you're wondering how I did the calculation, there's no pre-comp. We can just notice that our magnitude actually doesn't match here, so we can eliminate this. And also, in a right triangle, you have two angles that add up to 180, not 180, 90 degrees, right? So if we have A and B, the longer side, so this is longer, this is shorter. Since the longer side is greater than the shorter side, then we know that the angle of A is greater than the angle of B. So I know that it's definitely going to be a smaller angle and it has to be upward, so it's most likely B. I don't think this is actually tested on AICE physics. This is simply just what is it? I'm blanking, sorry. This is simply just a sanity check that's relatively quick. A sphere is released and falls. Its initial acceleration reduces until it eventually begins to travel at a constant terminal velocity. What does displacement time graph best represent? So terminal velocity is when you're falling, your velocity becomes constant. So then, since our velocity is constant, we can conclude that our displacement graph, or the slope, the gradient, the slope, is a line. So one thing we should note is that the sphere is released and falls. So that means that our displacement has to start from 0. So we can automatically eliminate A and B. And as it falls, we know that gravity is equal to negative 9.8 meters per negative second. So that means that it should actually curve upwards because it is accelerating, but then it will turn into a straight line as it turns into terminal velocity. So then it should be just B.